Welcome back to Further Solutions Academy. Further Solutions Academy. On this week video, I'll be walking you through inner product space. Inner product space. Before you view this video, try as much as possible to watch our video on vector. Very important for better understanding. It's a very nice topic. It's a nice course in mathematics. It's under algebra, advanced algebra, which is algebra 2 or 3. And the outline of this video, I'm working on the inner product space, which is the definition, length of a vector, and the distance in Rn. That is what I'm going to be working on as far as this video is concerned. Now, let me start from the inner product space definition. Definition of inner product space. Now, definition. Now, look at this. Okay, that is what we are talking about. Now, definition of inner product space. A real linear space, which is R, is said to be Euclidean if there is a rule assigning every pair of vector u and v, uv belongs to what? R. It means uv belongs to what? A real number. A real number called scalar product of what? Of the vector u and v denoted by what? This. This is how it's being denoted by. Such that, number one, it must be symmetric. Symmetric means when I have in a position u, also the same thing as what? And note this. This is always old when you talk about addition and subtraction. Addition and subtraction. Take note of this very well. Number two, this is symmetric. Number two, when you have this to this, can also be, at least when I have something like this, because I'll be emphasizing on this u, v plus w, it will be this multiplied by uv plus what? This multiplied by this, which is going to be what? UW. That is what I'm talking about. That is what this, for every UVW belongs to what? R. That is. Now, when I have a scalar, which is number 3, I have a scalar like this, you can bring out that scalar. For instance, scalars can be a value, can be a what? A number. Can be a what? A number, which I can bring out the what? The number. I can bring out the number from it. And that is what I mean by what? That. This is a scalar, these are what? These are vector, which belongs to what? Real, and this belongs to what? A value, which is a scalar. Now, this, for that to be a space, not this, for this to be a space, number one, it must not be equal to 0. If it is equal to 0, it means it means the there is no any distance cover, A space, this is a space. You get from here to here, become a space. Are you getting what I'm saying now? It's covering a what? A space. It must be greater than equals to what? A 0. It must not be less than 0. That's what I'm trying to say. Now, with this, we can now continue by saying that okay, that is all about our inner product space. Now, let me now use this opportunity to explain what is called length of a vector. Length of a vector. Now, when we talk about length of a vector, what we are trying to say is that okay, now when you talk about length of a vector, this is what we are trying to talk about. Now, when you talk about length of a vector, just notice that you are working in a line with magnitude of a vector. Now, it means you are talking about a value. Now, the length of a vector v in R with entire v1, v2, v3 is the non-negative scalar. Now, non-negative scalar is just like this. Now, when you have something like this, we'll be having you must not get a value that I've told you that a magnitude of a given vector is always equals to the given vector in a square and the root, which that is what we are trying to talk about here. That is what is called now. This is called the length of a vector, which you have this and you have this is equals to this and is equals to this. And a vector whose length is 1 is called what? Unit vector. I think we have talked about that earlier, which is I think by now, let me try to give example which you will be able to understand what I mean by. Okay, before we talk about distance in r, okay, that is distance in r of n. Distance in r of n. Now, when we talk about distance in r of n, okay, now lastly, before we go to exercise, now distance in r, which is r space, this is r space anyway. Now, let u and v be a vector in r space. The distance between u and v, written as distance of this, is the length of the what? Now, when you have to find the length of a given vector, final minus what? Initial. Now, I think it's very common in our physics time. Now, when you have to find the distance between initial and beginning and the end. Now, if here is final, here is the starting point, here is the ending point. This is m and this is n, and u. Distance, my distance will be equals to u minus m. That is what we are trying to work here. Now, when we talk about this in mathematics, now a mark of this, we call it norms. Please take note of that. It's called norms. I think at this point we are now working on space. We'll be working on along with norms and all those things, and you'll be fine with it. Now, permit me to write a very nice question so that you'll be able to see how vector space happen. Now, look at this problem. I have some problems here so that you'll be able to understand that area very well. Okay. Now, okay. Oh, thank God for Busola. She's the one that I went to demarcate the board. Now, Busola, I really appreciate you for demarcating the board. One of my very good daughters, she's there. Okay, I have something like this. Let me try to generate some problems here. Now, the question says that verify that uv space equals to 2x1 minus x1 y2 minus x2 y1 plus 4x to y2. Now, I want to verify this, and is what? Is inner product of R2. Now, why is it R2? Because the value we are given here, the vector we are given is just like x1, y1, x2, y2. Now, my R2 can be formed a two-dimensional 2x2 matrix, or two-dimensional what? Vector. Now, that is what I mean by what? R2. If it is R3, it means we are talking about x, y, z, row and column. I think we will talk about that when we're talking about bilinear function. We will understand that better. Now, I have this something like this, and I want to work on it. Now, the first thing I will explain now, you have to understand the four conditions I give to you. I wrote at the beginning of the video, which is the first one. If you are not having it, please go back to it. We'll be talking about the symmetric property. We'll be talking about when you open this function, like you open it, like you have a v u plus m. For instance, it means the same thing as what? U and plus what? Okay, m. I think I've explained that at the beginning of the video. And also I said that when I have something like this and something like this is a space. This is a space bracket. The same thing as lambda bracket of u and v. And also, if I have something like this, what else did I need? It must be symmetric. Symmetric means U M can also be equals to M U. It means position does not matter, and also M must be greater than equals to what is 0. Please, these are the things that I stated at the beginning of the video. Now, those are the conditions I will try to satisfy, I will try to work on as far as this problem is concerned. Once LHS is equals to RHS, it will be satisfied. I think that should not be a problem. For instance, if I'm to solve this problem, what I just need to do, I will just declare let U equals to x1, y1, V equals to y1, mean y, okay, sorry, 2, and y2, and equals to W equals to Z1, Z2. Now, that is what I will try to do. Since I have this, I can now say that, you know that if I have U, V, now my UV space, the same thing I'm talking about was X1, X2, and Y1, Y2. That is what I'm trying to do. This is equals to this. This is being represented by U, and this is being represented by what? By V. It will become a space when there is real and imaginary. And what you need to do, and you're going to be getting that. And now we were told that this equals to this. Now, since that is equals to this, I can now say that what? It will be symmetric if this can hold V, U. Now, what is the logic behind this? And this, you can see that position here, this U is first, V is second. But this time around, V will be first, and U will be what? Second. And you can do that, and you have it in the same form. It means that holds. It means that holds without any problem. I think this is what it's good to go. You have no problem with that. I think you have no problem with that. Now we can also see that my UV space will be equals to 2x1 y1 minus s2 y2 minus s2 y1 plus 4x2 y2. Now you can see that if I have it in form of VU space, the same thing as 2 y1 x1 minus y2. Hope I'm not making a mistake. Oh, this is going to be 1. Sorry. Okay, this is 1. Now y1 s2 minus y2 x1 plus 4x1, 4y2. That is, can you see that this is equals to this? That is what it means. First one is verified. Now the second one, the first one is verified. The second one, which we are talking about, okay, that is, it means my UV space equals to what? VU space. That is what it means. The symmetric property holds. The symmetric property what? Holds. The next one that we are to talk about is the second one, which I will be talking about. For instance, I can say that AU plus AW, it will be equals to AX1 plus Z1 Z2. That is what we are trying to work on. Now, since you know that, I can now continue by having AU plus, AU plus W, comma V. This will surely be equals to AUV plus, let me put B here to be very nice. Yes, let me put B. Let me just put B here. Plus BUV. Now, this can also be A bracket of UV plus what? The bracket of WV. Now, that is verified. That is being verified. Can you see that it's very, very simple, very, very nice. Now, you can see that it's very, very simple and it's very, very nice. You can now start your own manipulation and start manipulating numbers and start working and working and working. You will notice that you will arrive at 2x1 and 4x2 squared, because you are told that when you're having u, it will be equals to norms squared. That is very, very important. Very, very important. And with the norms, you can do whatever you want to do. I think the next video I will emphasize on that because of our time. I won't be able to touch that area next time. Now, in the next video, I'll be working extensively on orthogonal vector. With the help of orthogonal vector, we will be able to utilize this part very well. I think I'll be stopping here. Once again, I really appreciate you. Thank you for watching our video. Share among your friends and your classmates. Thanks for watching.
Bye.